Finite hypothesis class is very nice starting point to understand the sample complexity. So this is theorem for pack learning with finite hypothesis class. So let H be a hypothesis class and let epsilon and delta be greater than 0, in between 0 and 1. If a training set S of size n that satisfying this 1 over epsilon times log the cardinality of your hypothesis set plus log 1 over delta. So this is NH epsilon delta is drawn from your distribution D. Then with probability greater than 1 minus delta, every H in your hypothesis class with true error, LDF H strictly bigger than epsilon has training error non-zero. Okay, strictly positive training error. Equivalently, with probability greater than or equal to 1 minus delta, every hypothesis with training error 0 has true error less than epsilon. Okay, so in this theorem, we will show that if the true error is strictly bigger than epsilon, then all such hypotheses will have strictly positive training error with probability 1 minus delta. Okay, then from our assumption, we assume that H star belongs to our hypothesis class and H star satisfying the test error equal to 0. And since the test error of H star is equal to 0, which also imply the training error of H star is equal to 0, from that we can say that the training error of your empirical risk minimizer have to be equal to 0, right? So all the hypotheses having strictly bigger than epsilon training error make non-zero training error as well. So when test error is strictly bigger than epsilon, the training error also non-zero, then we can simply remove from the candidate hypothesis because there exists at least one hypothesis having 0 training error, and we are finding the best hypothesis for the training data point. That is empirical risk minimizer learning rule, right? So using this theorem, we can find the sample complexity. We can say some sample complexity, right? One nice thing of this theorem is this theorem only requires the cardinality of hypothesis, except that we don't use anything on the hypothesis class property. We don't care which hypothesis class we are using. We don't care. We just need the cardinality. When we know the cardinality and when we know epsilon and delta, from the cardinality we can simply say the sample complexity. With this amount of training data point, we can guarantee epsilon delta accuracy. So the proof is also very simple. How to show the sample complexity? Let's first define bad hypothesis. So what is bad hypothesis? Hypothesis having strictly bigger than epsilon test error. And then define bad event. What is bad event? At least one bad hypothesis having 0 training error. Since S is randomly sampled training point, LSH also a random variable, right? So we want to find some probability of such bad event. Indeed, bad event is a necessary condition for having this the strictly bigger than epsilon test error using empirical risk minimization ERM rule. Okay, so therefore, the probability, the test error strictly bigger than epsilon is less than or equal to the probability of the bad event. And the probability of bad event is, because the bad event definition is at least one hypothesis in bad hypothesis set satisfy zero training error. So this is probability union of the event LSH is equal to 0. So this probability is with respect to the randomness sampling the sample, the random sampling, constructing the sample set, the training set, okay, sample S. So here the LSH is a random variable and the randomness comes from the data generation process. Okay, and existence becomes the union of the each individual hypothesis training error 0. Right. And from the union bound, so here we use union bound. We can simply upper bound the probability of union by sum of each individual probability. And this individual probability simply is equal to the product of probability, because we are considering IID, random sampling process. Oh, this is just equal. Okay. And since our bad hypothesis having strictly bigger than epsilon test error, and we are considering IID sampling rule following D sample distribution, each individual probability strictly less than 1 minus epsilon. And we having product from I1 to n, so it becomes 1 minus epsilon power to n, and multiply by the cardinality of bad hypothesis. And the cardinality of bad hypothesis definitely is less than or equal to the total hypothesis cardinality. So basically we have this inequality, and from this inequality we just need to find n that make this, right? And that is this theorem. When n satisfies this, we can make this argument.